In 1900, Max Planck made a discovery so desperate that it felt almost blasphemous. Unless he accepted that the universe itself was somehow fake, the equations of physics simply refused to work. It was like leaning closer to a screen, only to realize that the breathtaking image you believed in was nothing more than crude pixels. Planck tried to convince himself this was merely a mathematical trick, just a way to force the answer to come out right. The world could not possibly be like this, but mathematics does not lie. In the end, his trembling hand wrote a constant beside the equation, a constant we now call Planck's constant. With it, he mercilessly exposed a truth. Reality itself has a resolution limit. If we travel inward, slicing matter down to 10 to the negative 35, the Planck length, reality disappears. That is the smallest pixel of the universe. Go any further, and there is no image left to render. The system fails. Physical laws break down. Time and space shatter. But this is only half the despair. If we travel outward, aiming our gaze beyond 93 billion light-years, we crash into the edge of the observable universe, a cosmic invisible wall. The speed of light limits how fast information can load, and the boundary of the map is fleeing from us faster than light itself. On one end, pixels too small to render. On the other, a horizon that will never finish loading. We are trapped between them. To see the full shape of this cosmic dragon, we need a ruler, one that spans 62 orders of magnitude, and the perfect reference object is already in your hand. Take this apple. More precisely, it floats at the most astonishing center of the universe. Inside it are about 100 million cells, made of roughly 10 to the 25 atoms, each less than a nanometer across. But that still isn't small enough. If we look at the smallest theoretical volume in physics, the Planck volume, you could fit about 10 to the 102 of them inside this single apple. That's a 1 followed by 102 zeros. Now, lift your head. If we used apples as building blocks to fill the entire observable universe, how many would we need? About 10 to the 84. Notice the problem? The microscopic pixels inside this apple outnumber the apples that can fit in the entire universe by an absurd margin. This is an extreme asymmetry. This 10-centimeter apple sits at a bizarre balance point, larger than the smallest pixel, smaller than the largest prism, perfectly wedged in the middle. Why are we in the middle? Hello, Earthlings. I'm Lao Ma. To find the answer, we're about to embark on an unprecedented journey. Using this apple as our origin, we will fall leftward into a microscopic abyss where even light cannot escape, and fly rightward toward a cosmic edge so silent it feels like despair. The birth of the quantum world. In 1875, a young Max Planck asked his mentor Philip von Jolly about the future of theoretical physics. Von Jolly replied that physics was essentially complete. All that remained was measuring a few decimals more precisely. At the time, this wasn't arrogance, it was consensus. Yet just 25 years later, this very student planted explosives beneath the foundations of physics and lit the fuse. That, it turns out, is the perfect recipe for a revolutionary. At the end of the 19th century, Planck tackled the last loose thread in physics, black body radiation. Why do hot objects glow? No matter how the equations were arranged, they produced absurd results. Cornered, Planck introduced a mathematical move he himself considered heretical. He assumed energy wasn't continuous like flowing water, but emitted in discrete packets. You can't buy half a quantum, just as you can't buy half an item. He called these packets quanta. At that moment, the old world collapsed. From this came Planck's constant, 6.626 times 10 to the minus 34. A number so small it feels hopeless, yet it is a ruler. On one side lies our familiar deterministic world, on the other, a probabilistic abyss ruled by chance. From quantum foam to the atom. At the Planck scale, space-time becomes quantum foam, boiling, bubbling, tearing apart and stitching itself back together. Wormholes flicker into existence and vanish instantly. uncertainty reigns supreme. Space-time itself twists, panics, and fractures. Climb back out of the abyss to something more familiar, the atom. Brace yourself.
Your apple is 99.99% empty space. Atoms are not miniature solar systems. They're ghostly probability clouds, rings, clusters, and gaps where electrons might be. You don't feel solidity because things touch. You feel it because electromagnetic forces repel. You have never truly touched anything. Every embrace, every kiss is a polite refusal by electrons. Forces, life, and emergence. The atomic nucleus should explode under its own electric repulsion, yet it doesn't. Enter the strong nuclear force, discovered by Hideki Yukawa. It is so powerful that releasing all the binding energy in a sandwich would flatten the city. Atoms are fortresses. Quantum rules set the floors. Electromagnetism fakes solidity. The strong force locks the core. Now comes the most astonishing scale of all: life. Here, the rules change completely. Mindless atoms somehow assemble into you. You are a universe made of atoms, and an atom inside the universe. Stars, gravity, and the cosmic web. When matter gathers beyond what electromagnetism can hold, gravity takes over. Welcome to the realm of stars. A star is a 4.6 billion year tug of war between gravity and nuclear fusion. And where gravity wins completely, black holes are born. The largest scale. The universe has an age, and because light is finite, we can see only part of it. We live inside a 93 billion light-year bubble, the observable universe. At the largest scale, everything becomes uniform. This is the mirror of the Planck scale. Total chaos below, perfect sameness above. Only in between do stories exist.
The apple, revisited. This apple, resting quietly on your table, is a miracle of probability. It is the intersection of 62 orders of magnitude. All four fundamental forces, strong, weak, electromagnetic, and gravity, converge here, on this apple, on you. We think ourselves small because the universe is vast, but perhaps this is precisely our purpose. You are the universe, learning to look at itself. Take a bite of the apple. What you taste is 13.8 billion years of history. So look up at the stars. Hold awe in your heart. Thank you for watching Entropy Files.